Scientists are analyzing a water problem beneath America that most people never see. In parts of the Great Plains, groundwater accumulated over thousands of years is being pumped faster than nature can replace it. In the Colorado River Basin, reservoirs are only about 1/3 full, and in California, groundwater loss has caused the land itself to sink. Today on DiscoverTube, we're investigating why parts of America's water system may look completely different within the next 35 years. And the biggest threat isn't simply drought. The water crisis is not one crisis. America isn't running out of water everywhere. That's the first thing to understand. The Great Lakes aren't disappearing, the Mississippi River isn't about to dry permanently, and rainfall isn't suddenly ending across the country. The problem is geographical. Some of America's fastest-growing cities and most productive agricultural regions exist in places where water is naturally limited. For decades, engineering solved that problem. Dams stored snowmelt, canals moved rivers across deserts, aquifers supplied farms during dry years. Pumps brought ancient groundwater to the surface. It worked so well that entire economies developed around water supplies that appeared permanent. Now scientists are discovering where the limits are, and nowhere is that clearer than underneath the Great Plains. The Ogallala, America's hidden water reservoir. Under parts of 8 states lies one of North America's largest aquifers, the High Plains Aquifer, often called the Ogallala. It extends beneath parts of South Dakota, Wyoming, Nebraska, Colorado, Kansas, Oklahoma, New Mexico, and Texas. USGS estimates its area at roughly 175,000 square miles. That's larger than California. But this isn't an underground ocean. An aquifer is rock and sediment containing water inside tiny spaces between grains. Think of a gigantic buried sponge. That's comparison number 1. Some portions are hundreds of feet thick. Others contain far less usable water. And that difference explains why Nebraska and Texas can sit over the same aquifer, yet face completely different futures. Before large-scale irrigation, groundwater had accumulated over very long periods. Then agriculture changed. After World War II, powerful pumps and center-pivot irrigation systems allowed farmers to extract water on a scale previous generations couldn't. Dry grassland became highly productive farmland. Corn expanded, cotton expanded, cattle production expanded because irrigated grain could support enormous feed operations. USDA says groundwater remains the dominant source of irrigation across much of the northern and southern plains, with the High Plains Aquifer at the center of that system. But there's one basic problem. In many places, withdrawal is faster than recharge, and you cannot pump water indefinitely when more is leaving than entering. The 2060 number. This is where the 35 years left headline comes from. It does not mean the entire Ogallala Aquifer disappears in 2060. The actual research is more specific. Kansas State University researcher David Stewart and colleagues published a major study examining groundwater use in western Kansas. Their modeling estimated that about 3% of the available groundwater had been depleted by 1960. By 2010, roughly 30% had been depleted. Under continued historical pumping trends, the model projected roughly 69% depletion by 2060. The research was published in the Proceedings of the National Academy of Sciences. That date is now only a few decades away. But even within Kansas, depletion isn't uniform. Some areas retain substantial saturated thickness. Others have experienced severe declines. The same pattern appears across the wider High Plains Aquifer. Northern sections, especially much of Nebraska, generally contain greater saturated thickness and receive more recharge. Southern sections in Kansas, Texas, and New Mexico are much more stressed. That's why saying the Ogallala has 35 years left is inaccurate. Some parts may support pumping much longer. Some wells are already becoming economically unusable. Water doesn't need to disappear completely before farming changes. It only needs to fall too deep to pump profitably. And that's already happening. When a well doesn't need to be empty to fail. Imagine groundwater sitting 100 feet beneath a farm. A pump can lift it relatively cheaply. Now lower the water table another 50 feet. The farmer needs more energy. The pump works harder. Costs rise. Then the well produces less water. Corn may require irrigation during exactly the hottest part of summer. If the well can no longer supply enough water during peak demand, the problem isn't theoretical anymore. The farm has to change. Some farmers reduce irrigation. Some change crops. Some move from irrigated corn toward sorghum, wheat, or grazing systems requiring less water. Others reduce planted acreage. USDA-supported research has examined what happens after irrigation becomes impossible. A 2020 study led by Gillian Daines and colleagues, titled Transitions from Irrigated to Dryland Agriculture in the Ogallala Aquifer, estimated that about 24% of currently irrigated high plains lands considered in the study could lose the ability to support irrigation by 2100 because of groundwater depletion. And not every irrigated field can simply become dryland farmland. The researchers found that some affected land also has soils or climatic conditions poorly suited to profitable dryland cropping. That means the transition isn't always irrigated corn becomes dryland wheat. Sometimes it becomes pasture. Sometimes production falls sharply. And that affects towns built around agricultural spending, equipment dealers, grain elevators, schools, restaurants, property values, jobs. The water crisis is also an economic geography problem. But groundwater isn't the only system scientists are watching. Farther west, another water source is entering one of its most difficult periods in modern records. The Colorado River's 2026 warning. In April 2026, the U.S. Bureau of Reclamation released a serious update. Colorado River system storage had fallen to roughly 36% of capacity. The river supplies water to more than 40 million people. It supports cities, agriculture, tribal nations, hydropower, and ecosystems across 7 U.S. states and Mexico. And the 2026 snow season made the situation worse. The Bureau reported the lowest winter snowpack on record across the basin. Lake Powell's minimum probable inflow for the 2026 water year was forecast at only 2.78 million acre-feet. That's about 29% of the historical average. This matters because the Colorado River begins largely as snow. Snow accumulates in the Rocky Mountains during winter. In spring, it melts. That water enters tributaries. Those tributaries feed the Colorado. So mountain snow acts like a natural reservoir. If winter snowpack is weak, less water may arrive months later. But scientists have found another problem: heat. Warmer conditions increase evaporation and dry soils. When snow finally melts, unusually dry soils can absorb more of it before water reaches streams. So the relationship isn't simply less snow equals less river water. It's less snow plus hotter conditions plus drier soils equals even less runoff reaching reservoirs. That is why scientists increasingly examine temperature alongside precipitation. The West just had a record snowpack problem. NOAA reported that by April 2026, the western United States had experienced its lowest snowpack on record. Arizona, Colorado, Idaho, Nevada, New Mexico, Oregon, Utah, Wyoming. All recorded exceptionally low April snow water equivalent conditions. This doesn't mean every year will look like 2026. Weather varies dramatically. One very wet winter can temporarily refill reservoirs and improve soil moisture. California demonstrated that after its extremely wet 2022 to 2023 winter. But one wet year doesn't erase decades of structural water demand. That's the difference between drought and water scarcity. Drought is temporary. Scarcity can be built into the system. If a region consistently uses more water than its rivers and aquifers can sustainably provide, even normal weather may not solve the problem. If you enjoy science stories about systems affecting millions of people, subscribe to DiscoverTube. And here's a question for DiscoverTube. Which is more dangerous, a river shrinking above ground or an aquifer disappearing where nobody can see it? Because California is dealing with both. California is pumping so much water, the land moves. California's Central Valley produces food on an enormous scale. But agriculture there depends on both surface water and groundwater. During wet years, rivers, reservoirs, and canals provide more water. During drought, groundwater becomes the backup system. Farmers pump harder. Groundwater levels fall. Then the landscape reacts. USGS has documented some of the largest human-caused land subsidence ever measured. In parts of the San Joaquin Valley, historical subsidence reached nearly 9 meters, almost 30 feet. That's roughly the height of a 3-story building. Comparison number 2. And this isn't simply the ground becoming lower. The aquifer itself can be damaged. Fine-grained clay layers underground contain water. When groundwater pressure falls far enough, those layers compress. Some compaction is irreversible. The aquifer permanently loses part of its storage capacity. So pumping groundwater during drought can reduce how much groundwater the system can store in the future. There's another consequence. Canals depend on gravity. Water needs a carefully controlled slope. If the land beneath one section sinks faster than another, canal capacity can decline. USGS has documented subsidence-related problems along the Delta-Mendota Canal and California Aqueduct. In other words, removing groundwater can damage the infrastructure designed to deliver surface water. That's a feedback loop scientists are now trying to manage. In 2025, USGS researchers published the Central Valley Hydrologic Model version 2, or CVHM2, as a tool for simulating groundwater, surface water, and subsidence under different management strategies. Scientists extended model scenarios through 2073, because the question is no longer simply how much groundwater is left. It's how do we use it without damaging the system we still need? Why America built farms in dry places. To understand why this problem became so large, go back to the 1800s. John Wesley Powell explored the American West after the Civil War. He studied rivers, topography, and rainfall. And he recognized something politicians often ignored. The West is dry. One important geographic transition occurs around the 100th meridian. East of it, precipitation generally increases. To the west, conditions become much more arid. The line isn't an exact climatic wall, but it became a useful way of describing America's transition from humid east to dry west. Powell argued that Western settlement and agriculture needed to be organized around water availability. Instead, much of the West developed under land systems created in wetter eastern America. Later, technology appeared to solve Powell's problem. Deep wells, dams, reservoirs, canals, massive pumping stations. Engineering allowed millions of people to live and farm in landscapes that could never have supported the same population using local rainfall alone. The Hoover Dam helped transform the Southwest. The The Central Arizona project moves Colorado River water hundreds of miles. California moves water from mountain watersheds toward farms and cities. The Ogallala transformed semi-arid grassland into irrigated farmland. For decades, this looked like victory over geography. But engineering didn't create new water. It redistributed existing water. And sometimes it used water accumulated thousands of years earlier. Why more efficient irrigation doesn't solve everything. Here's one of the strangest parts of the water crisis. Farmers have become much more efficient. Modern center pivot systems waste less water than older irrigation techniques. Subsurface drip systems deliver water directly near roots. Sensors measure soil moisture. Satellite imagery identified stressed crops. Precision agriculture can determine when and where water is needed. Kansas State reports that subsurface drip irrigation can reduce water use substantially compared with traditional systems. So shouldn't aquifer decline stop? Not automatically. Efficiency reduces the amount of water required per acre. But farmers may use the savings to maintain production, irrigate additional acres, or continue pumping for longer. Economists sometimes call this a rebound effect. The crucial measurement isn't just efficiency, it's total withdrawal. If the aquifer receives 1 unit of recharge while farms collectively remove several units, water storage continues falling regardless of how advanced the irrigation system becomes. The goal, therefore, isn't only producing more crop per gallon, it's bringing total use closer to sustainable supply. That is much harder, because water restrictions have consequences. Cut pumping and the aquifer lasts longer, but farmers may produce less. Farm income can fall. Local businesses lose revenue. Food production changes. That's why groundwater management becomes politically difficult. The benefits of conservation may arrive decades from now. The costs can arrive next season. The food connection. The High Plains isn't important because people drink directly from the Ogallala alone. It's important because of what the water produces. Corn, wheat, cotton, sorghum, cattle feed, livestock, dairy, food processing industries. The aquifer helped turn parts of the Great Plains into one of the world's major agricultural regions. Imagine an underground reservoir connected indirectly to supermarket shelves thousands of miles away. That's comparison number 3. You don't see groundwater when you buy beef, but water helped grow the feed. You don't see groundwater in a bag of cornmeal, but irrigation may have supported the crop. This doesn't mean grocery prices suddenly double when one well fails. Agricultural markets are more complicated. Production shifts geographically. Farmers change crops. Imports and exports respond. Consumers substitute products. But large, sustained reductions in irrigated production would change regional agriculture and could raise costs for certain commodities. The effect would spread gradually. That's what makes depletion easy to ignore. There may never be one morning when America wakes up and announces, "The water is gone." Instead, individual wells produce less. Farmers drill deeper. Some stop irrigating. A processing plant receives less local supply. A town loses population. An irrigated field becomes pasture. The map changes quietly. And by the time the change becomes obvious, much of the water has already disappeared. The race to use less. There are places showing that conservation can work. In western Kansas, local enhanced management areas, known as LEMAs, have tested groundwater pumping reductions. Farmers within participating areas agree to use less water over a defined period. Research has shown that meaningful reductions can be achieved while maintaining much of agricultural productivity through changes in crop choice, irrigation timing, and management. This matters because the Ogallala story isn't predetermined. The 2060 projection from Kansas State was not a countdown clock. It was a scenario based on pumping trends. Change the pumping and the outcome changes. That's the entire point of modeling. Scientists aren't predicting destiny, they're showing consequences. Use water one way and storage declines rapidly. Use it differently and more remains for future generations. The same principle now applies to the Colorado River. Current operating rules expire after 2026. Federal agencies, states, tribal nations, and water users are negotiating new rules for how shortages should be shared, because the old system was built around a river that often delivered more water than the modern climate is providing. About 3/4 through this investigation, here's another DiscoverTube question. Would you reduce agricultural water use now to protect groundwater 50 years from today? Because that is essentially the decision facing parts of the Great Plains. So does America have 35 years left? No, America does not have 35 years until it runs out of water. There is no single national water tank. The Great Lakes contain enormous freshwater reserves. The eastern United States generally receives much more precipitation. Some aquifers recharge relatively quickly, others do not. Some western cities have significantly reduced per-person water consumption despite population growth. Water recycling, desalination, conservation, groundwater recharge, and more efficient agriculture can all increase resilience. But the opposite statement is also wrong. There is no water problem. There clearly is. The Colorado River entered 2026 with system storage near 36% of capacity. The West experienced record-low snowpack. The southern High Plains Aquifer continues losing groundwater faster than natural recharge can replace it. California has physically sunk because of groundwater extraction. And models suggest major portions of irrigated agriculture may have to change if current pumping continues. So the real question isn't, when will America run out of water? It's, which regions will be forced to change first? For parts of western Kansas and the southern High Plains, that transition is already underway. Some wells are producing less. Some farmers are changing crops. Some communities are debating pumping restrictions. And the decisions made during the next few decades could determine whether groundwater supports intensive agriculture for another generation, or becomes economically unusable across much larger areas. Conclusion. More than a century ago, John Wesley Powell warned that America's dry interior couldn't be treated like the humid East. Technology allowed the country to postpone that limitation. We built dams, drilled wells, moved rivers, pumped ancient groundwater, and created some of the most productive agricultural regions on Earth. Now, scientists are measuring the cost. USGS monitors falling groundwater and sinking land. NOAA tracks drought, snowfall, and climate conditions. USDA studies how agriculture adapts when irrigation becomes limited. The Bureau of Reclamation manages a Colorado River system supporting more than 40 million people. And university researchers are modeling what happens decades into the future. The answer isn't that America has exactly 35 years of water remaining. It's more complicated and more important. Some water systems are stable, others are stressed, and some parts of the country are spending groundwater much faster than nature can replace it. Once deeply depleted, certain aquifers may take centuries or far longer to recover. That makes groundwater different from a reservoir. A wet winter can refill part of Lake Mead. It cannot quickly replace groundwater accumulated over thousands of years. So what should DiscoverTube investigate next? The Ogallala Aquifer, the Colorado River, or California's disappearing groundwater? Leave your answer in the comments. Subscribe to DiscoverTube for more science, geology, and environmental investigations, and we'll see you in the next documentary.